In addition to this, right, you can actually, a computational fluid dynamics is used for IC engine design also. How? So it is used for analyzing or simulating vaporizing and non-reacting sprays. What do I mean by that? So when you take a fuel and when you're injecting this fuel in a high temperature condition, right, that means it's going to vaporize. All right. And what does non-reacting mean? Well, the temperature is high enough that it vaporizes, but it does not combust. So what you will be looking at is, you will be looking at something like this. So this right here is your fuel spray. So your injector is going to be sitting here and the fuel is coming in. And as the fuel comes in, the red basically refers to the liquid fuel and blue basically refers to gas phase. So you can see that in the simulation, as the liquid fuel is coming in, it's actually vaporizing. Now this right here is a simulation. It's a computational fluid dynamics simulation. And on the right hand side, you have something called as Rayleigh scattering, which is basically an imaging technique. It's an experimental technique. And the nice thing is, the experimental images have been taken, the photos have been taken, and some image processing has been done on it to get this particular plot. So that is why this looks like your simulation. And you can see that it is very, very comparable, right? So that is the power of these type of simulations nowadays. You can get very, very accurate predictions. So can anyone tell me what is the advantage of doing this type of work? If I'm able to say simulate how the fuel is vaporizing, what is my advantage? It will not completely avoid experiments. It will basically minimize your cost. Say currently you're doing 10 experiments for each injector. If you're having an accurate simulation model, then maybe you can just do 5 experiments, right? So that is where computational tools are very useful. They help you reduce your testing cost. Now let's go to reacting sprays. So previously we looked at vaporizing and non-reacting sprays. That is, the spray will vaporize, but it will not combust. But now you are going to be looking at reacting sprays. How is it different? A reacting spray will first vaporize, and then because of ignition, after ignition delay, it will start to combust. So let's just play the video once, observe what is happening, and then I'll explain this one more time. And everything is being colored by temperature. Initially, the fuel is very, very blue because obviously your fuel is going to be at a much more lower temperature. The ambient is roughly at 800, 900 Kelvin. So when the fuel is coming in, it's going to vaporize. And as it starts to vaporize, the vapor temperature will increase because of conduction and diffusion effects. And then suddenly, in certain areas, the temperature starts to increase a lot. So for example, if you see here, the temperature is around 1400 Kelvin. So these are the regions where combustion has already started to occur. So this is how diesel engine combustion occurs, right? And then if I just play it a little bit longer, you can see that the temperature in those regions are starting to increase. Now it's much more visible. Now it's even more visible. Maybe I'll just delete these guys. And then suddenly you can see that the combustion development is also taken place or is being captured. So let's just let the simulations play for a while. And if I just stop the simulation, say at this point, there is something that's very interesting. So you can see that there is a particular length till which there is no flame. The temperature is only 600 Kelvin. So this is called as the flame liftoff length. Liftoff length. So whenever your flow is turbulent, that means there will always be a distance at which the flame will sit. Now this is why, you have people, for example, if you go to like carnivals, right, you will see people who breathe fire, right? This is exactly what they do. They basically have to spit the fuel in so fast that the flame will always not sit at their mouth, it will always sit away from their mouth. And that is why they're able to do it successfully. If they reduce the speed of their spitting, the flame is just going to sit at their mouth and it's going to cause a lot of injuries. Now, obviously, you're not going to be simulating that using CFD, but what you can actually do is you can use computational fluid dynamics and you can use these techniques to simulate how engines work. Now, let's just put it all together. So far, we have been talking about how you can simulate flows, how you can simulate vaporization, and how you can simulate turbulence, and how you can simulate combustion, right? Now you can put all of this together and actually simulate an entire engine. So for example, if I play this video, here you can see that I'm simulating something called as a tumble engine. So let's just play the video once, watch what happens, and then I'll explain it again. Okay, so that's basically the video. So let's play it again. So what's happening? So first, you can see that the fuel spray is being modeled, correct? The fuel spray is coming in, and what's going to happen is the fuel spray is going to come, and there's going to be this type of a flow pattern. That type of a flow pattern is produced because of the shape of your piston and also because of your intake port. Your intake port has a steep angle, right? Because of this steep angle, the flow is going to come in like this and it's going to spin around. This is what you call as a tumble port, T-U-M-B-L-E, tumble port. I hope that makes sense. So what I can do now is, let me just play the video one more time. The spray is coming in. You can see that there's rotation, and then after some time, the parcels, the spray parcels are slowly disappearing because they're vaporizing, and that's basically it. Nothing else happens after that because your engine, so for example, this color, right? This color indicates low velocity, and this right here indicates high velocity. So everything is colored by velocity. So that is why you are not able to see the spark event. All right, so now let me go to the next slide where it's the same video, but I'm coloring everything by temperature, except for the parcels. The parcels or the spray is colored by white color. So when the parcel comes in, it spins around and it vaporizes. So you can see that now there's no more parcels. And just before the spark, everything is mixed and then your combustion takes place. So let's just watch that one more time. There is vaporization taking place. Compression process is going to take place right now, and spark is going to fire. It fires and the flame propagates, and we are able to capture the temperature distribution. Now, what is the difference between CFD and an animation, right? Because if you go to YouTube, you'll be able to see animations like this a lot. But this is CFD simulation, meaning in simulation, you can actually get what is the temperature. So if I put a line like this, in any point, along this line, I can get the actual temperature, I can get the fuel concentration, I can get anything that I want. In animations, you won't be able to do it. Here I can calculate what is the maximum temperature, what is the minimum temperature. I can calculate how much NOx and how much soot emissions I'm getting from this simulation. It's very, very easily, you can calculate that very easily.